Okay, so let's look at this series here. Minus 1 to the k, of k over k squared plus 1. Okay, I do know if I look at this underlying sequence as k goes to infinity, that is going to go to 0. Okay, so it certainly looks like at least the alternating series is probably going to converge. So let's look first at the absolute value series, though. Let's look at the absolute value series and check absolute convergence first. Seems like it's probably going to converge for the alternating, but what about the absolute value series? That would be sum as k goes from 1 to infinity of k over k squared plus 1. And we need to check the convergence of this. Well, we could go to the integral test and do the integral of that thing, limit of the integral of that thing. It does set itself up okay to do integral test, and so that's an option. But I might actually do the comparison test. I'm actually use my limit comparison test. Because if I let k get really, really big, all that's really going to matter is k over k squared. K over k squared is related to 1 over k. So I'm going to compare this using the limit comparison test to the sum of 1 over k, which I know, being the alternating series, diverges. So I'm going to compare it to that. Because it compares, seems like it compares with the 1 over k, there's a big suspicion now that this thing is not going to converge, but let's do the test and see what it says. So remember, the way the limit comparison test works is limit as k goes to infinity. Limit as k goes to infinity of the top sequence, k over k squared plus 1 divided by 1 over k. Divided by 1 over k. That would simplify to be the limit as k goes to infinity of k squared over k squared plus 1. And again, the plus 1 is not going to really matter. So we're going to have limit of k squared over k squared, which is 1. And so since by the limit comparison test, the limit of the ratio is 1, means this is basically behaving exactly like 1 over k. They're on the same level. And so since the harmonic series 1 over k diverges, we can now say that this sequence, k over k squared plus 1, also diverges. So the absolute value one diverges. So that leaves us the question, what about the alternating series? Does it converge? What about the alternating series? Does it converge? So we turn back to the alternating series. The sum minus 1 to the k, k over k squared plus 1. Okay, so our terms, of course, are positive, so that checks off. Does the limit go to 0? Well, limit as k goes to infinity of k over k squared plus 1 would simplify to k over k squared. But k over k squared is 1 over k. As k goes to infinity, that does go to 0. So seems like the alternating series is going to work. There's just one further question we do have to address. Is this a non-decreasing sequence? We could look at the calculus, but here we can actually figure it out pretty quickly. As k gets bigger, k squared goes way faster than k. So k squared plus 1 is going to way outperform k. And so the top's going to keep getting bigger too, but the bottom's going to get bigger at a much faster rate, meaning that this fraction is going to keep getting smaller and smaller. And so therefore it is non-decreasing. And so by the alternating series test, this is going to converge. This is going to converge. Okay, so this converges, the alternating series converges. The absolute value series did not. The absolute value of it did not. So therefore, we're going to say that this series, the alternating series, converges conditionally. Converges conditionally. Okay. This converges conditionally.